Okay, so we want to define our system that we're thinking of when we're thinking about energy or heat transfer, right? Because we said energy can't be created or destroyed. And so in a system where we see, oh, the water was hot, but now it's cold, what happened to it? We have to think about how the energy is lost, or if a system begins to warm up, we need to understand how the energy, where the energy comes from. All right. So to do this, we want to have a strong definition of a system and its surroundings, right? So the surroundings, everything that's not the system. An open system means that energy can go back and forth between the surroundings and the system. And that's an example of having a hot cup of cocoa or any favorite drink you might have, right? Here's my hot cup of drink. If I leave it there too long, what happens?
It'll cool down.
Yeah. Where does that hot drink lose its energy?
To the cup.
Not my cup. My cup's a nice ceramic cup that doesn't get very hot when you put liquid in it, right? Or maybe you've heard of, flasks that have a vacuum separating region of a vacuum between the container where the liquid is and the outside. Then you don't feel any temperature, right? So it's not losing much to the cup. Where is it losing it?
I guess the air around it gets hot.
That's right. The molecules of water, because this is mostly water, whatever the drink is, collide with the air, and the air comes off, air that goes in there comes off a lot warmer than it went in. And that, it gradually is cooling down, losing energy from the solution. So that's like an example of an open system. But if I can close the system, if I can keep a vacuum around the whole thing, then the heat won't disappear. The heat won't disappear. Our energy of the system will stay the same. A closed system, generally you talk about being able to transfer energy but not mass. And an isolated or adiabatic system is completely contained, and no matter or energy can exchange from the system to the surroundings. Okay, so you have different ways of performing experiments. Endothermic and exothermic. Have you heard any of these terms before?
I've heard of exothermic.
What does exothermic mean?
It means to release heat.
All right, energy, and something that's exothermic is releasing, exit, out, right? Releasing energy. Endothermic means what?
Oh, the opposite, I guess.
That's right. It means that heat is going into your system. Again, from the surroundings, right, to the system. Or you could think about it from the reaction to the rest of the system. Okay? So here's an example. I have a cup of water, all right? And I'm going to put in my two reactants, A and B. And I have a thermometer here that I can measure the temperature of the water. And it starts here at 25 degrees Celsius. And then the water goes up to 85 degrees Celsius after A and B go in. Well, if I know that A and B are reacting to form some other compound, I can learn about the energy that is released from this chemical reaction by monitoring the change in temperature of the water. Now, to know how many joules of heat energy this reaction released, AB, right? A combining with B, to know how many joules of energy it released, I need to know how many, or the change in temperature, right? Because to change 1 gram of water, 1 degree Celsius, how much energy does it take to change 1 gram of water? 1 gram of water, 1 degree Celsius.
Oh, I can't remember, but that was a calorie. I think I remember that.
Okay, as a calorie. You don't remember what the number is?
No.
So it's 4.184 joules to change 1 gram of water, 1 degree Celsius.
4.184 joules?
That's right. okay? So if I want to know how much energy A and B released, I need to know how much water there was. And then after I know how much water there was, I need to know how much the temperature change was. And the change in temperature I can get by looking at the final temperature and subtracting it from the initial temperature. Delta, whatever, is always final minus initial. So my final temperature was 85. My initial temperature was 25. So that's a change of what?
60 degrees.
Very good. So I know my change in temperature is 60 degrees. And if I find out how many grams of water this is, I can know how many joules of energy I have, because, or how many joules of energy A reacting with B released, because it takes 4.184 joules to raise 1 gram of water 1 degree Celsius. So if I say that this is 100 grams of water and it raised 60 degrees Celsius, okay, so 100 grams went a change in temperature of 60 degrees Celsius, right? And there's 4.184 joules for every gram that changes 1 degree Celsius. This tells me how much heat energy was released by this process. All right, 4.184 joules for every gram degree Celsius, and grams cancel out here, and degrees Celsius cancel out here. So then I can take my 4.184 times 100 times the 60, and that'll tell me how much heat energy, or Q, was released by the reaction of A and B. Okay, did you follow that?
I'm going to push pause and go back and watch it again, but I think I got it.
All right, so it's good to watch again and try to help see if you can understand what's going on, but we'll do some problems going forward as well that hopefully will help you solidify that understanding. Generally, these kind of reactions we want to do in such a way that we don't have a lot of contact with the surroundings, because when this process occurs, some of the energy will be released to the air, right? And if the energy is released to the air, it won't change the temperature of the water, and then we'll think that A and B reacting actually lost less energy, right? Because we won't collect it with the temperature measurement change, because some was left or lost to the air. So these types of reactions, when we're trying to measure the amount of energy, we use a special instrument called a calorimeter, which will allow the reaction to occur in one sealed container here, so that all of the transfer of energy can be measured by looking at the change in temperature of the whole calorimeter. And we usually have an impeller, something that spins here, and what that's doing is it's allowing the water to circulate quickly, and so that the heat will be distributed amongst this container. On the outside here is is filled with water, right? Very good. And we can get what we call a heat capacity for our calorimeter. And now that means the heat capacity, kind of like 4.184 is the heat capacity that's not for a general cup of water, but that's 4.184 joules for every gram of water. So we call that a specific heat, but it's the same type of thing. It's telling us how much energy it takes to raise 1 gram 1 degree Celsius. Heat capacity is telling us how much energy it takes to raise the whole system 1 degree Celsius. So your heat capacity will differ for different systems. In the lab, often we'll just use coffee cups like this, nested coffee cups, because that is isolated enough, and the change in temperature there will relate very well to the whatever chemical reaction you're performing inside. So we can identify the heat that's transferred by taking the heat capacity, which is going to be a number of joules for every degree Celsius that the system changes. So the resulting heat will be the heat capacity times the change in temperature, where heat capacity is in joules per degree Celsius, and my heat capacity is degrees Celsius. So this is on the bottom, this is on top, these will cancel out, and I'll be left with just joules over here on the left for heat. Okay, so if I want to replace my heat capacity with just a system of one chemical, like water, then instead of having the heat capacity times the change in temperature, like I did here, I can have the mass of my water. So this is the specific heat of the water. This is the mass, and this is the change in temperature. Okay, so what I have here is another way of identifying Q, which is the specific heat times the mass times the change in temperature. All right, so both of these systems, whether it's using the specific heat times the mass times the change in temperature, or the heat capacity times the change in temperature, will give us heat energy, or joules of energy. Okay? All right. So let's think about this. If a cast iron skillet is moved from a hot sink to, or from a hot stove to a sink of water, which of the following is not true? The water is heating.
That happens.
The skillet is cooling.
Yeah, that's happening.
The heat transfer for the skillet has a negative sign. That means the skillet is losing energy. Is that true?
I think so. I don't know.
Well, if you think about the energy of the skillet initially, when it's hot, what's happening? What does it mean at a molecular level when a pan is hot?
The atoms are moving fast.
That's right. They're moving fast, so they have lots of energy. Then when something allows the pan to cool, that energy decreases. And if we kind of make a little diagram, we call these energy diagrams, and they're very handy to help us understand what's going on. So this is an energy diagram here. If I have an energy diagram that is going to plot energy, and this, you could just kind of think of this as time, or as the process, or we usually just write the reaction proceeds. This isn't really a chemical reaction. This is just transferring heat energy from the pan to the water. But if we say the pan has initial energy, energy initial, right there, and then after it's in the water, its energy final is down here, then if we want to look at the change in energy, if we took the energy, what do we do when we want to find delta E?
What do you mean?
Well, remember, delta whatever is always change, or the something minus the something.
Oh, final minus initial?
That's right. So we go energy final minus energy initial. And so we didn't actually put numbers on here, but we know that the energy decreases. So we could just throw some numbers on just to think about it for a second. If we put 10 and 1, then our final energy, 1 minus our 10, would equal negative 9, right? And so you're going to have a negative heat transfer if your system is losing energy, right? Or if the pan is losing energy. The water in this case, what is it doing?
The water is gaining the energy?
That's right. And so if you thought about the energy diagram for the water, we'll say this is for the pan. The energy diagram for the water, okay, it started there, let's say, but then what? This is the initial energy initial. Where's the energy final?
It's gaining, so it's got to be higher.
That's right. Energy final has to be higher because the water's gained energy. So now my delta E, energy final minus initial, is it going to be a positive value or a negative value?
How can I tell?
Well, let's just think about it. If this is final and it's higher than the initial, then if we threw a number in here like 10 and 2, then 10 final minus initial, that's delta E, right? Energy final minus energy initial. The difference would be what?
8.
Very good. Would it be positive or negative?
Positive 8.
Very good. So we're seeing that when a system takes on energy, then the change in energy is expressed in a positive value. Whereas a system releases energy, the negative value is what's associated with that release in energy. So the heat transfer of the skillet has a negative sign. That's true. Okay? The heat transfer for the skillet has the same side as the heat transfer for the water.
Well, that's not true. You just said that the water had a positive heat transfer.
Very good. Very good. So that one is our incorrect one. Let's look at the last one. The heat transfer for the water is equal in magnitude to that of the skillet. So what this is trying to say is that the amount of energy that the skillet lost equals the amount of energy that the water gained. Is that true?
Well, it probably lost some to the air.
That's true. That's true. But in general, if we try to assume that all of the energy is lost from one system, our skillet, to the other, our water, then all that energy that was gained by the water has to come from the skillet. Okay.